Our next speaker is Dr. Mark Rahmes. Okay, he's from Harris Corporation. And Mark has 20 years of experience at the Harris Corporation as an electrical computer engineer and a research scientist. Mark is a retired U.S. Navy Reserve captain and served 22 years as a commanding officer, engineering duty officer, and a surface warfare officer. He currently has 37 patents granted. Mark has published 26 conference papers at Harris Corporation. Mark served in the capacity of a principal investigator, chief software engineer, and a research scientist on various programs. Please join me in welcome Dr. Rahmes.
Good morning. My name is Mark Rahmes, and I'd like to thank Dr. Kalos for inviting me. This is a huge honor for me to do a keynote presentation to you all. I also thank my wife, Mary Jane, for being here. It's been a wonderful marriage with her. Well, we've had over 22 and a half years of marriage, and I thank her for being here. I want to talk a little bit about my co-authors. From Harris Corporation, I have Kathy Wilder, George Lemieux, Rhonda Henning, and then Dr. Kerry Balaban is in charge of the Brain Center at the University of Pittsburgh. Other members of our team who are not co-authors but have made great contributions are Dr. Kevin Fox from Harris, who works on big data analytics, and then from the Georgia Tech Research Institute, Dr. Erica Briscoe and C.J. Hutto. Dr. Briscoe also has done the non-blind review of this paper for this talk. And then, last but not least, Kendall Haven, who's a master storyteller, is part of the team and has contributed very significantly to this work. The work here is a biometric of neurobiology with influence with social informatics and game theory analysis. My outline is I'm going to talk a little about an introduction to the problem and the problem statement. I'm going to discuss story packets concerning structure of a story and communication. I'm going to talk a little bit about remote sensing, brain sensing, a new biometric spider chart. I'm going to talk about belief-dependent emotions, game theory with linear programming, and then some conclusions. The problem statement here is prediction of decision-making and influence patterns from neurobiological measurements of brain activity has recently become possible. fMRI machines measure the flow of blood in the brain, which is highly correlated to the neurons firing for the parts of the brain that show agreement or disagreement. And since we can detect the blood flow fairly accurately and they're correlated, we have a method of looking into the brain and the thought patterns. This talk talks about some new contributions. Currently no tool exists which can create a neurobiological packet theory based upon cognitive responses in a real-time manner. So the packet theory is very important, and I will talk about that. Modifying the messaging and communications to influence decision-making triggers or emotions based upon objective measurements, and determining the best possible message through game theory algorithms using belief category as emotions. And when I talk about belief categories, I mean there are belief emotions. So what is currently being done in the world? There is a very nice TED Talk out there by Reed Montague, who is working on a Roanoke brain study, which is very interesting. It's the largest study to date where he is neuroimaging over 5,000 healthy brains of people of all adult ages. He has teams in Virginia and London and is leading fascinating research in that area. 5,000 healthy brains will be the largest study to date. And until recently, the world's curiosity about brains has mostly dealt with abnormal behavior. And this begs the question, what is normal behavior? So that'll be a very interesting study that is ongoing. So what are we trying to understand? There is a structural MRI versus a functional MRI. Structural MRI reveals brain anatomy. And functional MRI reveals brain function. So here's a cartoon of Homer Simpson, and you can see what he's interested in. The question is, are we getting our message across to the right parts of the brain? So let's talk about packet-based communications. There's a narrator who sends packets of information to a listener. And equally important is that the listener returns feedback by body gestures or facial expression or words. And this cartoon shows an increasing level of interest from the listener back to the narrator. And those returning packets are very important because they steer the narrator's discussion to get the listener engaged. So there's a narrator, a comm pipe, content, packets which consist of information which can last from 1 to 30 seconds on average. Packets are not a continuous information of flow. There's pauses in a conversation, and there's times when the narrator is looking for feedback from the listener to gauge his story. And this paper is based on the premise that belief-dependent emotions can be triggered in the brain through a story or a narrative. And when I talk about a story, I don't mean a boring story. I mean a story that you internalize, one that causes you to think, that influences you, and that you remember. I did very much enjoy yesterday Professor Marlowe's talk about the issues with delivering a story and communicating in the hopes that what is communicated by the storyteller is received well by the listener. So here's an application of story packet structure to a sample story segmentation. Now, our master storyteller, Kendall Haven, has come up with this short narrative, which I'll talk about. John shook his fist and laughed at the burning sun. Wind swirled as he stretched out his hand, his trembling hand, breathed deep, and eased open the big double doors. He gulped and stepped inside. So as I read that, as the packets are delivered, the listener becomes more engaged. And there is an expected listener response. The response after packet 1 would be, there's an unexpected action, and that should build heightened awareness. And then after packet 2, you expect a smile or a chuckle. But packet theory focuses on the measurement of the story influence process and associated brain activity within packet boundaries during individual packets and the cumulative packets in the story. Packets represent only the delivery of the story, not the story elements. Packets are mapped to an expected listener responses and measured accordingly. And those packets are really the triggers in the brain which cause belief-dependent emotions to fire and the neurons to fire in the brain so that they can be measured. So we know which parts of the brain respond to stimuli, and we know how to manipulate those feelings in behaviors and beliefs, so then we can create a new biometric to determine human reaction to changes in a message. And that's what I show down here, and I'm going to talk about that next. According to Colin Kammerer, who has some nice work there out on the web on neuroscience and game theory, has talked about 8 different belief-dependent emotions: anxiety, shame, regret, joy, guilt, frustration, elation, and disappointment. These are the 8 major belief-dependent emotions. And in our system here, which we have not built completely, but we've tested individual pieces from end to end, we would envision a controlled or a controlled or human interactive feedback, maybe by a hand clicker from the listener to the storyteller, as well as a subconscious response measured by the fMRI. And it would be interesting to note how different the controlled and uncontrolled responses to the story can be. So belief-dependent emotions can be used as incentives or motivations and used to model behavior by applying psychological game theory. So as far as I can know, this is a brand new graphical biometric that can be used. Our solution links human emotion, packet theory, and game theory for determining optimal outcomes within communications dependent upon human belief networks. We use the Nash equilibrium to determine the player's worldview, from if the storyteller is the blue player and the listener is the red player. Rather than simply determining the best strategy for a blue player or the red player, we determine if you are a blue player or red player. And we create a new biometric for the controlled and uncontrolled bodily responses. So here's our system processing flow diagram. We start with the storyteller, who conveys a story to a player, and the player has an interactive response back, as well as a uncontrolled subconscious response measured by the fMRI. The Turing machine handles all those complex signals, stores the data, and delivers a very precise measurement to the biometric spider chart, and those 8 different belief-dependent emotions are the coefficients into the reward matrix. It is important to note that a training phase is definitely needed here to adjust the story and the reward matrix. Then game theory is used to come up with the value of the game and determine if the player is a red or blue player based on his worldview. So I believe this is all new. So what is game theory? Well, game theory is the study of rational behavior in interactive or interdependent situations. The bad news is knowing the game does not guarantee winning. But the good news is that game theory is a framework for thinking about a strategic interaction. Individuals and businesses use informal game theory all the time. And we are using game theory to study the rational and irrational behavior. Our solution integrates engineering, scientific activities for neuroeconomics and behavioral decision-making techniques. So game theory is part of decision theory, but there is a difference. And I like it in this cartoon, it's spelled out pretty well. 10 of you go to a restaurant, if each of you pays for your own meal, well, that is a decision problem. If you all agree to split the bill, well, now it's a game. And I see the waiter here in this cartoon say, "May I recommend the blue cheese for $10 more?" And the patron says, "Sure, because it's only $1 more for me." Check splitting policy changes the incentives. Never assume that others' behavior is fixed, and it's good to predict their reaction to your behavior. So what is truth or rational thought? Here is a list of the most controversial conversation topics, and each one of these can evoke very passionate conversations. And the more passionate you are or somebody is to these topics, the easier it is to determine what type of player you are. I mean, just watch the political talk shows. They can sure raise your blood pressure, whether you're a Democrat or a Republican or an independent. So why is it important to determine a player's worldview? Well, here we can use a player's worldview to look for insider threat, as in the case of Afghan recruits shooting U.S. soldiers. Also, I think it's very important that you can read on the internet that companies are hiring people and they're using emotional IQ or EQ. And they can use that by a questionnaire or videotaping an interview to look for body gestures and facial responses. What they're looking for is, are you the type of person who has an overinflated opinion of yourself? Or are you the type of person that's going to need constant kudos or encouragement to do your job? So that's very valuable. And recruiters are touting that that's the way of the future here, to measure your emotional IQ. And then if the eyes are a window to the soul, we can learn a lot about the Aurora Cinema shooting suspect, James Holmes. So it is very important to determine a player's worldview. So there's different types of learning game theory. Game theory is the formal theory of interdependent decision making. Classical game theory is a branch of game theory devoted to the formal analysis of how rational players should behave in order to attain a maximum possible payoff. Evolutionary game theory is a branch of game theory that studies the evolution of large populations of individuals who repeatedly play a game and are exposed to evolutionary pressures. Our focus here is really on learning game theory. It's a branch of game theory that studies dynamics of a group of individuals who repeatedly play a game and adjust their behavior over time. There is a number of different problems that can be solved with game theory. Game theory is not a silver bullet, and it can't be used for everything. But what game theory does allow you to have is a framework to measure the heuristics of how people solve problems. We have mainly looked at competitive, non-cooperative games with mixed strategies or pure strategies with a dominant or saddle point. And we can address all three of these situations with one design. Harder problems out there include game theory with imperfect knowledge, non-rational players, an asymmetric reward matrix. So let's talk about what is the Nash equilibrium. Well, a reward matrix exists such that an equilibrium point is one where reward is the smallest value in its row and the largest number in its column. So it's the max of all row minimums, and that equals the minimum of all column maximums. The left side is associated with the storyteller in our case, or the blue player, and that represents basic applied theory to decision making where you choose the best worst outcome. The right side, in our case here, is associated with the listener. And he is trying to use the minimax regret criterion so that he can minimize the maximum regret that he should suffer. And this is also called the Nash equilibrium. And we're going to use it here as simply the threshold. Whether your score comes above that or below that will determine if you are a red or blue player, depending on your worldview. So there are 8 different belief-dependent emotions, and the rows in this reward matrix are associated with what's often called the blue player or the storyteller, and the columns are associated with what is often called the red player or the listener. Let me say it's not that in this case, this is a non-cooperative game, it's not that the storyteller is out to get the listener. It's simply a score is trying to determine if you are a red or blue player. And we know which parts of the brains perform what functions. The lateral prefrontal cortex on the left and right sides of the brain, as well as the anterior insula, determine unfair situations and often are associated with disagreement. And in back of your brain is the visual cortex. That is usually associated with agreement. So we have the tools and the visualization capability to measure agreement or disagreement within a brain. I've taken this picture here from Colin Kammerer. There has been a study done where giving to charity or good moral behaviors increase brain activity. And it has been found out that paying more taxes does not cause a healthier brain signal. I would say here that the Lord loves a cheerful giver, and He rewards the faithful with a healthy brain. Let's talk about an example of a belief-dependent reward matrix. So I've populated this reward matrix with some values that are typical of those found out on the internet with some examples. Notice that the matrix may have sparse values since some emotional responses would not be expected. And some emotions are annotated with values of 0 and would be considered irrelevant outliers. Now, one very important part of future work here, which I am not sure of the answer yet, is how often do you need to change the reward matrix within a story? Is the reward matrix good for the whole story, or is it good for only portions of the story segment? That is future work, and that definitely needs to be researched. So here we can solve using a mixed strategy, and I used Lindo here to come up with what are the most optimal emotions of those 8 belief-dependent emotions for this reward matrix. So this equation here, this linear program, is correlated to the reward matrix, and we can solve for the blue player's highest score. And it turns out if we want to solve for the red player's highest score, it's simply the dual of the blue player's linear program. So in this case here, based on that reward matrix, it turns out that the highest score for the blue player would be to expect a response of frustration. But for the red player, the highest score based on the dual of the blue player would be elation or frustration. And the player score is simply compared to the Nash equilibrium to determine if you are a red or blue player. In this case, it's not necessarily true that the red player is trying to get a high score. It is what it is, and that will determine if the listener is a red or blue player. So accuracy. It has been shown that an fMRI can detect brain activity with 70 to 85% accuracy with a low false alarm rate. So I am mildly optimistic that this system will work. It is true that individuals are very complex and different from each other, and each individual can have a different attitude on any given day or a different diet on every given day, and that may cause the system not to be as robust. But that is what we are trying to look at. Other applications using game theory. I think I still have a few minutes, but I have applied game theory in a real way to other domains, and recently I've been working on using game theory for optimal pixel labeling from satellite imagery, which is really what I really do at Harris. I've been employed at Harris for over 20 years, and my forte is image processing. I found very little on this topic with real images. I have submitted this paper based on the next 2 slides to the American Society of Photogrammetry and Remote Sensing, which I will be presenting in October in San Antonio. But this is new. Input imagery comes in. You can create a truth data from the imagery, and you can use supervised classification to come up with the land use land cover features. You can treat each pixel as an independent player, and you can use a reward matrix based on land use, land cover classifications versus supervised learning to decide what is the best label for that pixel. Can do an accuracy assessment and then put an output map. So here I show some satellite data. I show a training set. The idea here is to put in the values from the supervised learning into this reward matrix, where the rows are the land use, land cover, and the columns are the different supervised learning classification algorithms. I have 4 different supervised learning algorithms. One is a decision tree, one is support vector machines, one is Bayes, and one is k-nearest neighbors. If we wanted to, per pixel, decide which is the best land cover label, we can use game theory. And so far I'm finding pretty robust results using this. And then the Nash equilibrium applies also. That can be used for change detection. So what I've found so far is if you use game theory, treating each pixel as an independent player, you can take the best of the best based on the supervised learning algorithms and come up with a composite map which so far is getting better results than each of the individual supervised classification algorithms independently. So I only have seen work on this with cartoon images, nothing real. So I believe this is new and a real application towards game theory. Anyway, in summary, for the neurobiological analysis of narratives that influence an audience, we have come up with an end-to-end system which bridges research in social, computational, cognitive, and neurosciences. Our method provides an integrated quantitative roadmap for experimental analysis of behavioral dance between a narrator and listener. And then the packets also provide a target for detecting underlying brain activity in both the narrator and the audience. We have defined a solution for determining strategies based on game theory using a graphical method. Automated game theory is promising for solving real-world strategies to help the warfighter make decisions of resource management and planning activities. Tomorrow afternoon, I'm presenting a session talk on how to populate a reward matrix automatically from open source data for the purposes of resource management and planning activities. And there's a critical need for actionable information for threat prediction. And then I have some references here for my talk. And I appreciate your attention, and thank you for having me.